Welcome back to Lesson 8, Year 10, Physics, Electrical Circuits. This is the 8th and final lesson of this topic, electrical circuits. So let's firstly look to see what the learning objectives are for the lesson. They come in two parts. The first one is understanding the relationship between energy, power and time. And the second one is a different relationship between, which is an electrical relationship between power, voltage and current. So the pages we're covering, 45 to 52. If you can please turn to page 45 in your booklets and write lesson 8 and the date at the top of the page as shown here on your screen. So a quick recap on electrical appliances. We've learnt about different forms of energy and energy transfer previously in science. As it says in the paragraph at the top, appliances transform electrical energy into other forms. In the spider diagram below are two appropriate appliances next to each circled word. I'll start off with light, and for light I'm going to write down two appliances that transfer electrical energy into light. So I can do bulb and TV. Of course, the TV, not only does it transfer light energy, it also transfers sound energy. Now, what you need to do is do exactly the same for heat, sound and movement. Remember, movement is the same as kinetic, just a different word to describe movement energy. Now this next sentence that I'm about to highlight here is really at the heart of this lesson. Power is the rate at which an appliance transfers energy. Energy is measured, remember, in joules. Energy, so the unit of energy is joules. Symbol capital J. Power is measured in watts, capital W. But crucially, and this is what we'll be working towards, energy. No, let's think of it another way. Power is the amount of energy used every second. So, if a TV was using 300 joules every second, which we write down like that, we simply say the power of the TV is 300 watts. If you understand that, that's the main concept of this lesson already understood, and well done. But what we're going to be doing next is applying that to two different calculations. One which actually is power is energy over time, but also then looking at how we can calculate the electrical power when we know current and voltage. Okay, diagram A. One bulb has a power rating of 15 watts, the other 38 watts. Look at the two bulbs. Yeah. I think the second question is asking which one's which. Well, this is the 38 watts because it is producing more light energy per second than this one here. I think it was 15 watts. It's brighter, produces more energy, therefore more energy per second, I should say, therefore it has a higher power rating. What's the transformation, the energy transformation in both bulbs? Well, electrical energy is turned into light, which is the useful energy, and wasted energy, heat. Which bulb converts or transfers more electrical energy per second? Well, you can answer that. Which bulb has a higher power rating? I've already explained that to you, so if you don't know the answer straight away, rewind the video and go back to about a minute ago. In fact, the 38 watt bulb transfers, I'll do this one, 38 joules per second of electrical energy, and the 15, let me just check it was 15, yeah, 15 watt bulb transfers 15 joules per second. Please remember to go back up, and wherever you see the red asterisk, so that's question 2 and 3 in this case, you answer those. Also, I've marked these previously for you to do, question 5 and 6. I'll go through question 5 with you. The garden strimmer has a power rating of, look up above, you've got to convert that 0.6 kilowatts into watts. Just remember that 1 kilowatt equals 1000 watts. So how much is 0.6 kilowatts? Oh, yeah, 0.6 kilowatts in watts. Wasted, you should be able to work out what's the wasted energy. Remember, the useful energy is what you want the appliance to do or to convert energy to. The fly mower there, you can see, is strimming the grass. So in order to trim that grass, you've got a piece of cord coming out, which is rotating around and cutting the grass. Now that grass isn't cut by the sound of the fly mower. That's wasted energy. It's not cut by the heat of the fly mower. That's wasted energy. It's cut by the movement of that cord. Kinetic energy or movement energy. Get used to using the word kinetic energy. That's the correct scientific terminology. So you do question 5 and 6. Moving on now then to power ratings. All appliances transform a certain amount of energy per second. This is called a power rating and is usually measured in watts or kilowatts. Let's have a look, before we do this next activity, let's have a look at the label you'd expect to find on an appliance, such as, well, it wouldn't be a washing machine at 87 watts. That could be a television, for example. Or is it television, like 60-inch? There's the screen size. So and what you've got at the top here, we'll be learning more about this later on in the course, how energy efficient the appliance is. So this has got a very high, the highest, in fact, of power ratings. It doesn't waste much energy. And again, we'll be learning more about energy efficiency later on in the course. Anyway, let's look at this. In this column, you put in a number, 1 being the appliance with the highest power rating, and 6 being the lowest. So if you think, for example, that the television's got the highest power rating, you would put a number 1 there. If you thought the kettle has a lowest power rating, you'd put a 6 there. So, oh, by the way, those aren't the answers, or certainly aren't going to be the answers here. So what you need to do now is pause the video, and then in your booklets, write down numbers 1 to 6 in that column. Now you should have filled in that predicted rank column. You compare against the actual power ratings of the appliances, and you can see the kettle's with the highest power rating at 3000. The lowest one in this instance is the Xbox at 135 watts, and then working our way from top to bottom in terms of power rating, or highest to lowest, I should say. Wash machine is second, tumble dryer third, microwave fourth. Oh, I've got the Xbox wrong there, haven't I? That's fifth. And the TV is sixth. 87 watts. Okay, and that 87 watts is taken from here. Now the conclusion is for you to do, but I will read through and give you a helping hand. The appliance that transferred the most amount of energy was the kettle. Its power rating was 3000 watts, or 3000 joules per second. We can say its power rating was also, I'll let you do that. You've got to convert 3000 watts into kilowatts, and you put that answer in there. Question 1 underneath. Before I do that, let's just go through this here. In physics, the amount of energy an appliance transfers per second is called its power rating. Yeah, we've already talked about that. So power can be measured in joules per second. So joules per second just means the same thing as watts, the amount of joules transferred per second. It just so happened that physicists agreed to make up a new unit called watts. Question 1. What did the appliances that had a high power rating all have in common? Well, if you think of the kettle and the wash machine and the tumble dryer, they all produced heat. But you'll also find an appliance that produces heat and movement or kinetic energy, they generally produce the most energy, or transfer the most energy per second. That's why they have the highest power rating. Now, underneath, something for you to do, and I've made a start on it for you. Take any 4 of the appliances, and they're written down there for you: microwave, kettle, tumble dryer, Xbox. Complete the table to show how a power ratings can be shown in 3 different types of units. So if I just do the microwave one for you and you do the rest. the power rating of the microwave is 800 watts. That can be written down as 800 joules per second, or 0.8 kilowatts. Therefore, what you need to do is that row, and that row. Underneath, a couple of predictions for you to make. So don't worry about if they're not spot on. Doesn't matter. It's going to be almost impossible to know exactly how many joules are going to be used, but we're going to calculate that in a moment. It asks, which transfers more energy, a light bulb on for 1 hour or the same light bulb on for 20 minutes? Well, I hope you get that one right. You should get that one right. You can say common sense, or you can just think of a formula we're going to be using. Energy is power times time. So the longer something's on for, the more time you have, the more energy is being used. Which transfers more energy? A kettle on for 3 minutes or a light bulb on for 4 hours? I'll let you make your predictions underneath. And you can think again of this equation here when you're doing that. So just pause the video now and answer questions 1 and 2. Moving on to page 48. New equation. Again, this equation will be given to you in your exam. Energy is power times time. And if you need to rearrange a higher tier pupils, it's useful to write it down like this, where, remember, if you covered E, it leaves you P times T, power times time, or power. So if you covered P with your thumb, that would leave you with energy over time. And T would leave you with energy over power. This can also be shown, the rearranging of the equation, that is, using this Focus e-learning software, which is available via the school website under the pupil area. And it has, on the left hand side, all the different equations that would be needed for physics, GCSE, that's year 10, year 11 and triple science. So don't feel as if you've got to learn all of those. You won't have to, but if you look part of the way down here, these are the two equations we're going to be using today. E equals P times T, P equals V times I. So if we click on E equals P times T, it just shows an alternative way to rearrange that equation. Bottom left, you see that triangle method, and it says that it says there, one way to remember the arrangement is to use a diagram like the one on the left, cover up the letter you want to rearrange, that's the one I just showed you, or use the algebraic method at the top, and you can just click through the different stages, dividing by T, cancelling T out, and so on. And so you choose whichever method you prefer, and up the top here you can change to rearrange for a different variable. In that case, that was T. In the case here now then, for the kettle and the lamp, it's asking which transfers the most energy. Well, in order to work that out, we use the equation E equals P times T. And in these equations, we've got to work in kilowatts. So we've got to transfer, or convert, I should say, 3 kilowatts to 3,000 watts. And we've got to be working in time, in seconds, not in hours. So we've got to convert 4 hours into seconds. The way of doing that is if we put time in brackets, so it's 4 hours, and in each hour we've got 60 minutes, and each minute we've got 60 seconds. It's just a matter then of putting that into a calculator. So I'm just plugging in those numbers into the calculator. I'm going to double check that again in a moment. And remember, that's joules. I just checked that, that's correct. So 43,200,000 joules. That's the amount of energy that the kettle would use in 4 hours. Now then, I've made a mistake, haven't I? I've used the 4 hours for the kettle where I should have used 3 minutes. Okay. So what I can do there is change the time to 3 minutes, which will be 3 times 60. I thought it was an awful lot of energy, so apologies there. Let's just change that. And before I forget, make sure I put the correct values in for the lamp. The lamp itself, I think it was a 20 watt lamp. Let's just go back and check. Yeah, 20 watt lamp, so it's 20 times 4 hours. So this time in brackets, we put the 4 times 60 times 60. And then use a calculator to work both these out. Pause the video and can you please calculate the energy for the lamp? You should have got 288,000 joules. So you can see the kettle, even though it's on for 3 minutes and the lamp on for 4 hours, you use a lot more energy using the kettle. In fact, a plug-in appliance cannot have a higher power rating than 3 kilowatts. And that's because domestic circuits at home, in schools and buildings, on the ring main circuits, have a capacity, a maximum current that can flow through the wires for safety reasons, which is 13 amps. And we'll be finding out in the next part of the lesson that if you go above 3 kilowatts, that means that you'll be going above 13 amps. Therefore, that's why you can buy kettles at 3 kilowatts but no higher. You can buy electrical heaters at 3 kilowatts and no higher. Okay, so check you've got those correct answers and just write the conclusion underneath. So the conclusion would be something a conclusion should be answering the question, and the question here is, which transfers more energy? So all you've got to do in the conclusion is write down the kettle transfers more energy than the lamp, and use the evidence then. That's the values to back that up. And just out of interest, it's almost, if we divided 540,000 by 288,000, let's try that again. It's almost, you can see the kettle almost uses twice the amount of what the lamp uses, but not quite. I'll just let you read this information below. We've covered that, so there's nothing new there. Question 1. A kettle transforms 1,800 joules per second of electrical energy into heat. Not 3,000 joules per second, so that's a kettle with a lower power rating. It's not 3,000 watts or 3,000 joules per second. It's less powerful. It would take longer for the water to boil. You just have to be a little bit more patient when you're waiting for your cup of tea or coffee or hot chocolate. Other beverages are available. Question 1. The kettle's power rating is, now in watts, that would be 1,800 watts. And if you convert that into kilowatts, you simply divide by 1,000. Bobby's curling tongs have a power rating of 680 watts. How much energy is transferred if they are left on for 124 seconds? So you go back to the equation, get into good habits, remember about the importance of writing down the equation, then the numbers, then the answer, then the units. E for equation, N for numbers, A for answer, U for units. Sounds a little bit like Eno. I'm sure I've told you this before, and I always think of Eno the donkey. That's supposed to be a donkey. Eno, equation, number, answer, unit. You've got to remember that to get the full mark. So there's our equation. The power is 680. Oh, I made a mistake here myself. I should be highlighting the important information. You know, the fact that the curling tongs and the fact that Bobby owns a curling tongs is not important to answer this question. To answer the question, what's important are two things. P the power and T the time. So P is 680 and the time is 124. Let's just plug that into our calculator. And remember the units, of course, joules. Equation, yes. Numbers, yes. Answer, yes. And units, yes. So that's how you get your full marks. Question 3. A room has 260 watt light bulbs that are left on for 5 minutes. How much energy is transformed? You can do this one, but just remember, please, that the power isn't 60, it's 2 times 60. It's going to be 120. And left on for 5 minutes. you need to convert. In fact, I'll do this one. I'm feeling generous. I'll do this one, and I'm going to leave you then do some of the others. Now, because it's for 5 minutes, you've got to convert minutes into seconds again. Now, to do that, we need a power of 60. That's the easy bit. 5 minutes. So I'll put the time in brackets. 5 minutes and there's 60 seconds in each minute. Now, I suppose what I should be doing if I'm following the BIDMAS rule, even though they're all multiplied together, I should do in brackets first of all. So 5 times 60 is 300. Double check that. Question myself now after making an error earlier. Yeah, 300. And you multiply that by 60. 18,000 joules. Question 4. I'm definitely going to let you do this one. And 5 are for you to do. We'll have a quick read through. I'll give you a couple of hints if needed. Remember, highlight the important bits. You'll have to convert kilowatts to watts. And there's your time. So that's your power. That's your time. And scaffold it slightly. And you put your values into the equation. Question 5. How long does Callum play on his Xbox for? Ooh, right now then, what we've got to do this time is rearrange. We'll come on to that in a second. What do we know? We know the Xbox has got a power rating of 135 watts and the total energy is that. Now when you rearrange the equation, T equals E over P, or energy over power, you're going to have to put in power at the bottom, 135. The energy at the top was at 2.43 million. And that will give you an answer in seconds. But for a further challenge, I'd like you then to convert it from seconds into hours and minutes. So if you divide the number of seconds by 60, that'll give you the number of minutes. And then you could divide by 60 again to work out the number of hours. I'm assuming Callum has been on his Xbox for a significant length of time, i.e. it's more than a few seconds. Okay, I'll leave that one for you to do. And just remember, work out in seconds first of all is the main challenge, and then if you do hours and minutes, that would be great. So the final part of this lesson, the final part of this topic and booklet, of course, is using this equation. So it's tying together what we've learned about power, current and voltage. And there's a simple equation that we can use. Power is current times voltage. Just a quick recap before we make a start. Power's measured in watts. Let's try that again. Current is measured in amps, or I'm not sure whether they want you to put down the symbol or the units, but I've written down the units here. That's the units. Watts for power, amps for current, V for voltage, and these would be the symbols. Rearranging, power is current times voltage. So if if we wanted to write down power, we've already got that down. I is P over V, P divided by V, and V is P divided by I if we need to rearrange. And again, you could use that piece of software I showed you earlier if needed. There's nothing being asked you to do that. I'm sure we'll be using that information in a moment. So if we look at the electric drill, for example, it's telling us the current is 2, the voltage is 240. Oh, just an aside here. The 240 volts. Now, in the UK, 240 volts was the mains voltage level. Over the last, I think it was about 10, 15 years, even longer ago than that, I'm showing my age now, it's changed from 240 voltage down to 230 volts. Now, you need to remember that for the exam, and you will be learning a lot more about this when you do domestic electricity later on in year 10. 230 volts, 230, sometimes I call it dentist voltage as a way of remembering. 230 or 230 volts. But we'll use the values that are there. Oh, and I did promise as well that I'd explain to you why the kettle, or any appliance in fact, can't be more than 3000 watts. If we rearrange the P equals I times V, I is P over V, maximum power 3000 watts, and we divide that by 230 volts, then what we should find is that it comes to a value of around about 13, just over 13 amps, 13.0 amps. If we had an appliance more than that, it would be dangerous, and the fuse in the plug, the 13 amp fuse in the plug, would blow, meaning you can't use the appliance. And we're going to be using, or learning I should say, more about that later on in year 10. Anyway, thought it'd be interesting to mention. Complete the table by labelling the heading box with the appliance name, and underneath calculate its power. Okay, I've done the first one, the bulb, which is this one here. I'm going to do the toaster next. So you write down the name of the appliance. You have to flick back and forth between page 50 and page 49. You've been asked to work out the power of the toaster in watts and in kilowatts. So in watts, first of all, current 3 amps, so 3 times 240. So that would be 3 times 24 is the same as 6 times 12, so that will be 72, so it'll be 720 watts. Obviously you can use a calculator to make sure. Can you check that please? 720 watts, 0.72 kilowatts. The others are for you to do, and then just tick them off as you've done that. Okay, getting harder. Let's see. What I'm highlighting now is something you would find characteristically, typically on appliances. So this one's taken off, I think, an iron. You can see there's a few things to note here. That It's designed to operate between 230 and 240 volts and at 50 hertz. So that would work in the UK. In America and other countries, they have different voltage levels for main circuit. The power rating is there, right, between 1850 and 2000 watts. Metal plates like the one on the left are attached to modern electrical appliances. For example, an iron use the highest voltage but lowest power value to calculate the current flowing through the iron to 2 decimal places. If you're in an exam or you're at home now and you've got to calculate the current, the first thing you ask yourself, what do I know and what equations can I use? Well, let's highlight just using a voltage, calculate the current, and use a power value. The equation we've just been given, the new equation is this. Again, you'll be given that in the exam. And if you rearrange that, I equals P divided by V. It's a use the lowest power value, that's your 1850, and the highest voltage value, 240. Then you divide one by the other. I just use a calculator there to work that out. I'll give the answer then to 2 decimal places, so that would be 7.7, round up that 0 because you've got 8 after it, 7.71 watts. Okay, if we look at the next one, it's a 4 marker, so just remember to go through the right process. You've got to work out the energy transferred by, I will scaffold it slightly, energy is power times time. So you need to do question 2. We've learned about standard form earlier in this booklet, so you can do 2B. Question 3. An iron switched on for a long time at the mains never transfers its maximum theoretical energy value. Well, I'll give you a little clue there. It's because it's more than a clue, is the answer. You have some energy is wasted and is transferred into other forms of energy, and is wasted not on ironing the garments, the clothes, but is wasted to the surrounding air, heats up the surrounding air. Okay, then what we've got left, we've got page 51 and page 52. Calculate the resistance in this toaster. So this is a bit of retrieving prior knowledge. We've got to work out first of all the resistance. R equals V over I. Remember that, you can answer that because you've got your V and you've got your I here. So it's another one for you to do. Question 2. So far you've used that formula, P equals V times I. To calculate the power of an appliance, there is, however, I can see there's a typo there. That should be there is. There is, however, an equation you could use. P equals I squared R. Now don't worry too much about where that comes from. I'll quickly show you now. P equals I times V. If you substitute for V And I'll change the colour. So rather than writing in V equals I times R. So we multiply that by I times R. So I times I is I squared. So it's just two equations. This is just two equations in one. Two become one. Use both equations to confirm the power of the toaster. Well, you can do that one. I'll do this one because it's a new equation. The current is 3, so I do 3 squared times R. Oh, we need to work out what R is first of all in order to do that. Well, you can do that. You get your value from R from question 1 and you put that in here. And you should find that the answer you get here and the answer you get here are the same. Question 3, the vacuum cleaner above has a resistance of 34 ohms. 34 ohms. Calculate its operating current to 2 decimal places. This is where you really need to think. You ask yourself, what do I know and what do I need to know? Well, you do know you've got a couple of equations that involve current. P equals I times V. You also know that V equals I times R, or I equals V over R. Now if we look at the information given, we're given power. We're also given resistance. So we can't work out the current from that equation there because we need to know V. If I rearrange P equals I times V, I equals P over V. Again, we don't know V. So this is where we can use this equation. P equals I squared R. I squared equals P divided by R. So what you're going to have to do in this equation, if we just use that, P over R, and you square root both sides, like that. Here's your P, here's your R, and you substitute your P and your R into that equation, work out the current. So that's quite a challenging question. Question 4, electric toothbrush is a power rating. Again, get your highlighter out, 1.2 watts. Current flowing is 0.4 amps. Calculate the resistance. You can do that. Provide the answer to question 4 in kilo ohms. Yeah. And that is that. That is the end of this first booklet. First of 5 booklets for Year 10 Double Science Physics. And I would say by far the most challenging of the 5 and by far the longest of the 5. So if you have understood and followed this work, you are doing fantastically well and are on course to achieving really high grade at the end of Year 10. So well done. Give yourself a pat on the back. But please, please, please make sure you completed all the assessments on Moodle that go alongside this booklet. Go back through your booklet and check that everything's complete, ready for giving in to your teacher to be checked over and marked and for you to have good, meaningful feedback. So, well done, and just make sure you've completed those assessments. I'll see you in the next topic. Bye.